Stacks are a common programming data structure, and many programming interview questions require knowledge of stacks. Tanishq has helped thousands of people prepare for coding interviews, and now he's going to help you understand the stack data structure by demonstrating how to solve a bunch of common coding interview problems. The problems go from easier to harder, and Tanishq will be guiding you the entire time.
My name is Tanishq Chaudhary, and I'm very excited to bring you this course on stacks. So let's go ahead and get started. Hello everyone and welcome. Let's talk about the implementation of stack. We are going to start off with a couple of examples to understand the reason why stacks are built in first place. Then we'll look at the implementation level details of stacks in terms of Python and C++. Alright, let's get started. Now if I ask you the question, what do you see on the screen? You might reply that there looks to be a couple of books present on a shelf. So you can call this a stack of books. Now, what would you do if you had to read the first book, the book on the top of the stack? Well, you want to read Harry Potter, so you will just pull it out of the stack, you'll remove it from the stack, you'll read it, and then you'll push it back onto the stack once again. Now, this is simple and fine, but what if you want to read Grokking the Coding Interview now? What do? Of course, you can try pulling it out from the middle, but all of these books are dense and heavy. And you don't really want to disturb the balance of the elements on the top of the stack. So what you can do is, you can take out the first book, you can take out the second one, and then finally read Grokking the Coding Interview. You read it, and then you can put it back on the stack, along with these two books. What we have just seen is a very important property of stacks. That is called the LIFO ordering. LIFO stands for last in, first out, saying that the elements that come into the stack towards the end, that is, the elements that come in the last, are the first ones to get out. Last in, first out. Now this is a property that will exploit again and again throughout this entire series. It's going to be a central property, and it's the heart of the reason why we use a stack in many of these questions. Now let's go ahead and formalize the operations we can do on the stack, because we know that if the LIFO ordering is being followed, we have to use a stack. But how do we exactly use it? Well, let's look at a couple of operations. The first operation we saw was removing items from the top of the stack. We call this operation formally the pop operation, because we are popping the elements out from the top of the stack, right? So this is going to be the pop operation. The second operation we saw was to add the book back onto the stack. In other words, we're looking at a push operation. Push is the formal term used to define, saying that we want to add an element onto the stack. In other words, we'll push an element on the stack. Now there's a final operation that we do very commonly, and that's the peek operation. Now the peek operation simply says, hey, go ahead and take a look at the top of the stack. Go ahead and take a peek at the top of the stack. Right? So these are three operations that we'll keep in mind. All right, so now let's go ahead and actually look at how these are implemented in terms of Python and C++. Java implementations are pretty close to both of them. So even if you understand just one implementation way, you'll be able to do it in any other language. I've ensured and tried my best to make sure all of the codes are language agnostic. They can be easily translated from one language to the other without having a lot of issues. All right, so let's go ahead and actually look at how we're implementing these. The first thing is, how do we initialize the stack? And in Python, we're going to use the list implementation of stack because there is no inbuilt internal class for it. We're going to create a list, empty list of our own to initialize the stack. In C++ there is, so we're going to use stack, and we're going to have a stack of int variables and we'll call it s. Pretty simple. All right, how do we push? In Python, we do stack.append. And so we can do stack.append an item, and this is going to return a none value. That is, it does not return anything. We just append this element onto the top of the stack. In C++, we simply do s.push. This is going to return a null. All right, how do we peek? How do we check what is the element at the top of the stack? Well, in Python, the way to do that is to use stack of -1. That is, it is going to give you the last element on the top of the stack. Right, so in this case, it's the element 3. How do we do it in C++? We simply do s.top. Now remember, this is a slight terminology difference, but nothing much. You want to look at the top of the stack, you want to peek at the top of the stack, this is how you do it. All right, how about pop? In Python, you do directly stack.pop, and that is going to return your value 3. This is a crucial difference, by the way. In Python, you're going to get a return value of 3. However, in C++, when you do the pop operation, you're not going to get any return value. All right, this is super important, especially when it comes to implementation. Keep the language specific details in your mind. All right, the last thing which we'll also very commonly use is to check whether the stack exists or not. In other words, is the stack empty or not? So in Python, we can simply use the stack variable, and that internally checks its length. So in our case, we appended one element, we checked the top of the stack, and then we popped it out. So the stack is currently empty in both the cases. Now, if you just use stack, if you say if stack colon blah, 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 that is going to return a value of false because the stack is empty, right? In C++, we can do s.empty, which is a function that is going to work on the stack variable, and it's going to return true, saying that, you know what, the stack is indeed empty. So again, small implementation level details that you have to keep in mind. All right, so now that we have a better understanding of how do we implement stacks, let's go ahead and take a look at a real life test case where stacks will be very helpful to understand. Hello everyone and welcome back. In the previous video, we talked about how to implement stacks in terms of C++ and Python. In this video, we're going to take an example problem, simplify path to build up our understanding of stacks further. In fact, this question is present on both LeetCode and InterviewBit and has been asked in companies' coding interview rounds many times. This in fact forms a basis for a very important point, that how stacks are being used in the real world as well. All right, let's go ahead and get started with the formal problem discussion. So we're given a path, and this path is a Unix path given to us, and the goal of this problem is to return the canonical path. Now, if you're not familiar with how paths or Unix-based paths work, I'm going to link to resources down below so you can check them out first. Anyways, we're given a path and we have to follow 4 conditions to return a canonical path. First, we have to start from a single slash. This slash represents nothing but the root directory. Second, any 2 directories are separated by a single slash. So we can have directory 1 slash directory 2 slash blah blah blah. Condition 3 says that we should not end with a trailing slash. In other words, the slash at the end of it, if there is a slash at the end of it, you have to return it. All right, fourth condition, which is the most important one. It says that it only contains the directories on the path from the root to the target. That is, there is no period or double period directories. Now, period and double period have special meanings. Period basically says that wherever you are, stay. That is, whatever directory you are on currently, just stay over there. Double period means take a step back, right? So whatever directory you are on, take a step back. All right, let's try to formally build up our intuitions and our logic. All right, let's take a couple of examples to understand this better. First things, we have a slash home slash as the input. The blue is the input and the green is the output, which by the way is a common coloring scheme I've followed throughout the rest of this series, so you don't have to worry about anything. All right, so we have slash home slash, and what is the output? The output is slash home. That's because we have a trailing slash at the end of the input, which we remove. All right, let's go ahead and take another example. In this case, we have slash dot dot slash. What it means is we start from the root directory and we have to take a step back, because dot dot really means that you have to take a step back from the current directory. And then we have a slash at the end. So of course you can remove the slash at the end because it's a trailing slash. But now this double dot means that from the root directory, we have to take a step back. But there is no step backs from the root directory. The root directory is where you start. So in fact, this will simply be reduced to staying on the root directory. That is, from the root, if you want to take a step back, you'll end up at the same root. All right, let's take another example. And this time we have slash home slash slash 1337 slash dot slash. First things first, remove the trailing slash. Now what? We notice that between home and 1337, there are actually 2 slashes. What does that mean? Well, in our case, the implementation level detail is that if there are multiple consecutive slashes, all of them will be useless basically, and we only have to consider one slash. In other words, multiple slashes will get compressed to a single slash. So we have /home/1337. Note that the period at the end now means that we have to stay at the current directory. So we were at 1337 and we stayed at 1337. Let's take a look at one final example, which is going to be the most important one. And this has sort of all of the conditions mentioned in the question. So let's go ahead and formally try to break this down to get the logic. First things first, we start off with a single slash, which is going to be a root directory. This is by default present in all the test cases. We have to start from the root directory. Now what's the next step? We want to go to the next value, which we see is home. Now what does home mean? Home means that we have to go one directory forward. That is, from the root, you have to go to home. All right, so pretty simple. But now you get a dot dot. What does this mean? This means that you have to take a step back, which means that from the root, you first went to home, but now you have to take a step back and go back to the root. All right, pretty simple again. What next? We get a dot dot once again. And since we are already at the root, taking another dot dot simply means that go stay at the root. All right, so now we get a /tmp. And what does that mean? That means that now we have to take a step forward. We have gotten the directory. And so we'll go to /tmp. And then we have a bunch of slashes together, that we have two slashes that just gets compressed to one single slash. And then we have a dot. Now dot simply means that wherever you are, stay. So we were at the /temp directory and we'll stay over there. And of course, the last slash at the end is just a trailing one. So we'll remove it. In other words, the final answer we get is /tmp, as we saw in the first line of this slide. So now let's go ahead and formally talk about how did we do this? How are we going to implement this going forward and going backward thing? If you have guessed it, yes, you are right. We have to use the data structure stack. Of course, this is a playlist about stack. We have to use a stack. But why do we use it? Again, whenever we have a directory like home or /tmp, we have to take a step forward. And whenever we have dot dots, we have to take a step backwards. And a good way to simulate that is by using a stack. All right, let me go ahead and show you how this formally works out. So the first thing we get is home. So home means that we have to move forward, which means that we will push the value home onto the stack. That is, we'll append this value to the top of the stack. Now we get a dot dot next. What does that mean? That means that we have to go back one directory. In other words, we have to pop the element out of the stack. All right, we get a dot dot once again, but the stack is already empty. What do? This is a special condition, and we have to say that, you know what? If the stack is empty, you can't really pop anything, and we don't really have to pop either. We were at the root and we'll stay at the root. So the stack remains as is. Then we have tmp. So what do we do next? This is a directory. So we append it. We push this value on the top of the stack. Now we get a dot. What does that mean? That means whatever directory you are at, stay there. In other words, the stack remains unchanged. So if we have to formalize, what can we say? Let's focus on the core parts. First things first, how do we start? The way we start is at the root, and that is nothing but the queue to initialize the stack. Right? Whenever we start, we're going to initialize the stack. Now directory means taking a step forward. What does that mean? That means that we're going to append an element onto the top of the stack. In other words, we are going to push this directory on the stack, right? And what does dot dot mean? Dot dot now means that we have to pop. We have to go one directory backward. So whatever you appended, just pop it back again. And then finally, we have a dot, which means that we really do nothing, do no operations. And this is really it. This is it for the logic of this problem. Let's go ahead and look at the optimized solution, and we're going to code it up from scratch. All right, let's go ahead and look at how do we implement this question in terms of Python code. The first thing we'll do is initialize the stack to be an empty stack, and then we'll start to iterate over the directories in the paths. Now, obviously, the path given to us is going to be a string, which is separated by these slashes. So each of them directories That is, any two directories are separated by a single slash. So we have to say, go ahead and do path.split by the slash. That is, get me the individual directories and we'll see what to do next. So what's the first condition we saw? Remember from the code, remember from the logic. The first condition we can say is that, you know what? If you get a dot, that is, if you get the operation where the directory we have to move to is a dot, that means that, wait, don't really do anything, right? We don't really do any operation on the stack if we get a single dot. Right, what's the other case? Well, if the directory is what? If it's a double dot, what do? If it's a double dot, we have to do an operation called pop. That is, we have to go back one step. We have to pop the element from the top of the stack. So we'll do stack.pop. But now is a very important edge case, right? This is a very important condition I'm going to write. See, it's not always the case that you can pop this directory from the stack. That is, for stack.pop to work, you have to ensure that stack is not empty. Because if the stack is empty and you pop an element out of the stack, that is going to give you an error. Whether it be Python or C++ or Java, all of these languages are going to give you an error if you pop an element out of the empty stack. So first we'll go ahead and check, hey, you know what? If the stack exists, only then go ahead and do the stack.pop operation. What do we do else? What do we do otherwise? Well, in case the stack is already empty and we get a double dot, what does that mean? On an empty stack, which means that we are at the root, and we get a double dot, which means that from the root we have to move a step back, which means that we just have to stay at the root. So the stack remains as is, and this condition, in the else condition, we don't really have to do anything. All right, what's the final case? What the final case is, say that go ahead and append this value to the stack, append this directory to the stack. All right, so this is it, right? We're going to return what? Well, one of the conditions, the first condition in the question says that the path starts with a single slash. So we're going to go ahead and start with a single slash. And since we have all the directories in the stack, let's go ahead and do the join operation. So we'll do join.stack. So what this is going to do is iterate over all the elements in the stack and join them with a slash in the middle. All right. So before we go ahead and run this code, by the way, there's one more condition that is important to know. See, because directories can have a case where we have, say, double slashes, that is, if we have slash home slash slash foo slash, these double slashes are going to give us an issue. Because when we split this path by slash, it means that there is going to be a case where there is one slash and then there's an empty string and then another slash. In other words, what I'm saying is we have to add one more condition saying that if the directory is actually empty, that is, if there were multiple consecutive slashes, then we don't have to do anything either. Right? If we get multiple slashes, we just look at it as one slash and we don't really do anything. All right. So this is it for the logic of the code. And let's go ahead and test this out on a bunch of input test cases. It looks to be correct. So let's go ahead and submit this. And we get it accepted. All right. So this is it for the solution to the problem, simplify path. Hello, everyone, and welcome back. Let's talk about the problem min stack on InterviewBit. All right. So the goal of this problem is to design a stack that supports a bunch of operations. First operation, push. We have to push an element X onto the stack. Very simple. Second operation, we have to design an operation that returns us the top of the element. That is, it is going to see what is at the top of the stack and return it. Third operation, we have to design a function that pops the value out of the stack. We have to remove the top element and return it, right? So all of these three operations up till now are something we've already seen that are like the very basics of what a stack is. But now there is a fourth operation given to us, getMin. This function is going to return a value X which is going to be the minimum value of the entire stack. Now, the only constraint that is given to us is that all of the queries should run in constant time. That is, they should take order of 1 time each. Now, how do we start to think about a solution? Well, since the problem is about using a stack, let's go ahead and create a stack, and we'll start to see what do we do once we get the queries. All right, so this is the simulation we'll run. Let's say we get the query to push the value 7 onto the stack. So now this is how the stack is going to look with the value 7 on top of it. If we get push 3, we'll just add 3 to the top of the stack. We get push 9, we add 9 to the top of the stack. Now let's go ahead and say that we get the query getMin. What do we do at this point of time? GetMin query says that go ahead and get the minimum element of the entire stack, which means that a naive way to proceed about it is to go over all of the elements inside of the stack one by one and find the minimum value. In this case, we find that 3 is the minimum value, so we'll go ahead and return 3. Now let's say that we get another operation called pop, so we'll go ahead and pop the element out of the top of the stack. Then let's say we get getMin again. Again, what are we going to do? Iterate over the entire stack, go over all of the elements one by one and return 3. We realize that 3 is the minimum value, right? So let's go ahead and say we get another value, another operation, push 1. So we add 1 to the top of the stack. GetMin says, well, get me the minimum value of all the elements in the stack, which means that the value will be 1. Now, if you realize what we have been doing up till now is all of the operations like push and the pop, even the top, are going to take order of 1 time to run, as it does in normal stack. However, the getMin operation is kind of a pain. That is because we have to iterate over the entire stack one by one, taking order of n time, where n is the number of elements in the stack. This means that there has to be a better way to do it. We have to figure out a way to answer the getMin query in order of 1 time. Alright, so let's go ahead and talk about the optimized solution. This is one of those questions where if you don't know what to do, you really would have no idea on how to proceed. And in these kind of questions, what we're going to do is we're going to create another stack. That's right. We're not just going to have one stack. We are going to have 2 stacks. The first is the blue one, which we already saw, which will handle the queries like push and the pop on the top. But we will also have a green stack, which is going to keep a track of the minimum value we have seen up till now. Let me go ahead and show you the simulation once again, and that will make a lot more sense, because it's a beautiful way to approach this problem, right? So let's go ahead and say we get the query push 7. We get the request to do push 7. So we'll just add 7 on the top of the stack. Now, this is the stack we're going to append it to. We're going to add it to the blue stack directly. Whatever query we get, we directly apply it to the blue stack. The green stack will simply reflect the changes of the blue one. So since we added 7 to the stack, the minimum value of the stack is now 7. So we'll add 7 to the stack. Now let's say we get a push 3 operation. What do we do? Because this is a blue case, we'll simply add 3 to the top of the stack. But we'll have the 3 reflect changes in the green stack as well. That is, the green stack is now going to store a value that is the minimum of 7 and 3. Because we have 2 elements on the top of the stack, right? So we're going to have minimum of 3 and 7, and so we'll store 3. Now let's say we go ahead and get the value as, let's say we get a push 9 operation. Now the top of the blue stack will have 9, but the top of the green stack will have the value 3. And that is because 3 is the minimum value of 3 and 9, which is going to be the minimum value of the entire stack. All right, so now what do we do? Now if we get a query getMin, what do? We'll simply look at the top of the green stack and return that as the answer. We are not going to pop out anything at this point of time, right? As soon as we get a getMin query, we are going to peek at the top of the green stack and return that value. Now let's say we get a operations which says go ahead and pop the element out of the stack. So this is going to pop the element 9, and now we have to make the green stack reflect changes of the blue one. Since we removed an element, we will also have to remove the element from the green stack. Now, what if we get a getmin query once again? If we get a getmin query, we'll simply look at the top of the stack. And since the value is 3, we'll return 3. All right. So now let's say we get a push 1 operation. What do we do? 1 gets directly pushed onto the pushed onto the blue stack, and the green stack is now going to reflect the changes. Green stack is going to have the value, the minimum of 3 and 1. That is, it is going to take the minimum of the previous element on the top of the stack and the one which we got currently. All right. So now if I get min again, what do we do? Look at the top of the stack and return 1 as the answer. All right. So this is really it for the logic of the code. What we have done is we have figured out a way to implement the solution using 2 stacks. So let's go ahead and initialize, and let's go ahead and create self.stack, and we'll have self.minStack, right? These are the 2 stacks that we initialize. This is the green one and this is the blue one. All right. Now what do we do when we get a push query? The stack that we have, the blue one, is simply going to reflect the changes directly. So we'll say when we get a push operation, self.stack.append x, nothing special. But what do we do about the min stack? Min stack is going to reflect the changes. So I'm going to say self.minstack.append. Well, I want to append the minimum value of the current x. That is, I'm going to take the current value and find the minimum with the min stack top. So we'll go ahead and do the min stack, find the top value and take their minimum. Right? Pretty simple. This is exactly what we discussed before. But now we have to take care about one thing. This is a common thing which we have to take care across all the stack questions. See, what we have tried to do here is that we have to try to access the -1 element on the min stack. That is, I want to find the top element of the min stack. But this will only work. When will it work? This will only work if the self.minStack is not empty. But if it's empty, what do we do? Look, if it's not empty, we'll simply take the min of x and the top of the stack. But if it's an empty stack, let's just go ahead and directly append this element to the min stack. So we'll do self.minstack.append x. All right, this makes sense. So now what do we do when we get the pop operation? Remember, we have to ensure that all of the changes in the stack are reflected in the green one as well. So when we do self.stack.pop, we have to do the pop operation for the min stack as well. Again, one more edge case, one more condition. You can only do pop when? You can only do pop if the stack is not empty. So we'll say if self.stack exists, that is, there are elements inside of the stack, then you can do pop. But if the stack is empty, pop will really do nothing. So we'll just say it's pass, right? Now what do we do when we get top? Again, here we have to return what is value at the top of the stack. So we'll do self.stack -1. But wait a second, it is not guaranteed that the self of stack of -1 is going to exist. In other words, the stack might be empty. So if self.stack exists, well, then you can go ahead and do this. But what do we do otherwise? The stack is empty and we're asked to return the top element of the stack. Well, look at the condition. Condition in the question mentions something. What should top do on an empty stack? Return -1. So in this case, we are going to return -1, right? What do we do when we get min now? Remember, in the top function, we return the top of the stack, which is the top of the blue stack. But in the getMin function, we're going to return the top of the green stack. So we'll say if self.minStacks exist, well, then you can go ahead and return the self.minStacks top. But if it does not, go ahead and return -1. You can see that there's a lot of parallels between getMin and the top. That's because the only thing that changes is the stack. In top, we use the blue stack, and in the green one is used in the getMin function. All right, let's go ahead and test this out quickly. Looks like this is correct. So we'll go ahead and submit this. All right, we get it accepted. And this is it for the solution to the problem, min stack on InterviewBit. All right, that's it. Hello everyone and welcome back. Now this is after our first section on where we discussed the stack related questions, where we built up our understanding of stacks, the implementation level details, along with a couple of example problems to help us understand things better. In this section, we're going to focus on parentheses related questions, which is actually going to be a step up from the previous one and is going to lead us to calculator related questions in the next section. Now, why are we talking about parentheses questions in the stack playlist? You will get the questions answered very soon. What we're going to look at is a bunch of example problems like valid parentheses, longest valid parentheses, redundant braces, and many more. These are commonly asked in interviews, and applying stacks to these problems becomes a crucial part of understanding stacks themselves. All right, now we will go ahead and take a look at an example and we'll try to build up our understanding of parentheses related questions and calculator related questions later on. Because what we're going to understand is the reason why we use stacks inside of these parentheses questions in the first place. All right, so given this expression to you, let me ask you the question. If I give this to you on a paper and I'll give you a pen to solve this, how would you go about solving this kind of expression? The first thing you would want to do is look at the innermost brackets. That is, the innermost brackets contain the value d. So let's go ahead and evaluate that first, right? We want to focus on the innermost first and then slowly zoom out to the outermost. Now, what do we do zoom out to? We would zoom out to b minus d in the next step. And this would then finally lead us to the entire expression. What we have done is nothing but parsing. Now, parsing is a fancy word for what it means is we have to figure out the structure of the input. That is it. Parsing means to figure out how the input is laid out. Now, why do we want to understand the structure of the input? Why is this kind of thinking helpful? Let's take a look at a simple example. We'll take this simple example, and in this case, we have two opening round brackets and two closing round brackets. Now, if I ask you the question, can you tell me what is the corresponding opening bracket to this current closing round bracket? That is, I've highlighted this closing round bracket for you. Can you tell me which of these is the corresponding correct opening bracket? Pretty simple to answer because we already know the way we do this is by taking the bracket that is the closest. We figured that this opening bracket came in the last and was the first one to get resolved. Wait a second. The bracket which came in the last was the first one to get resolved. That is, we're following something of the sort of a LeetCode ordering. That's right. This is the reason why we use stacks in these parentheses questions. Because when to use stack is answered whenever we see a LeetCode ordering, right? So we have seen that we have to use a stack in parentheses questions and in calculator related questions as well. But how exactly do we use it? How do we use stacks in these kind of questions? What we are going to do is we are going to do a left to right parsing. As I explained earlier, parsing is a fancy word. What it simply means is we have to understand the structure of the input. We have to break it down step by step and understand, okay, this is what gets resolved first and this is what gets resolved later on. Now, left to right simply means that we're going to iterate from the left to the right. Okay, enough talking. Let me actually show you with an example. So this is the example case we took earlier. And we have initialized an empty stack on this. All right, so what do we do next? Well, here's a rule that you have to keep in mind. Anything that you get, which is an opening bracket, a character like A, B, C, D, or an operator like plus, minus, division, multiplication, anything of that sort you get, you simply append it to the stack. That is, you push everything except close brackets on the top of the stack. Here's what I mean. Say we get this opening round bracket, we do nothing but push this on the top of the stack. Then we get A, push it on top of the stack, then we get plus, open curly bracket, B, minus, open round bracket, D. The only time when we do not append items on a stack is when we get a closing bracket. This is important. This is very important. If we get an opening bracket, a character or an operator, whatever, we directly add it to the stack without thinking, without having second thoughts. But as soon as we get a closing bracket of any kind, we have to start thinking. All right, so I already asked you the question of what this closing bracket actually closes. What is the corresponding opening bracket? And if you see in the stack, we actually have that value with us. We have this opening round bracket on the top, on this stack here. However, that is not the top element. And it might not always be obvious which of these opening brackets am I closing, right? Because currently we have a closing bracket in our hand and we want to figure out, hey, what is the area that I close? What is the area? What is the expression that needs to be resolved first? Because I'm following the leaf ordering again. So what we do is we'll keep on popping these elements off the top of the stack till we see a corresponding opening round bracket. Here's what I mean. As soon as we get this closing round bracket, we'll go ahead and start looking for the opening round bracket. So we'll pop out D because D is not an opening round bracket. And so D is sort of in an intermediate state. We don't really know if D is part of a valid expression or not. So we'll just keep it hold. Right? Now what we get? On the top of the stack, we see that there's an opening round bracket. What does that mean? Currently, look at the yellow marker. We are at a closing round bracket. And on the top of the stack, we have found an opening round bracket. In other words, everything inside of both of these brackets is going to get resolved. Both of these brackets satisfy each other, both of them resolve each other, and everything in the middle of them will get satisfied. So D is actually part of a valid string now, right? The brackets are balanced in a way. All right, so now let's go ahead and look at what happens later on. We'll keep on iterating and we get a closing curly bracket. Now what do we do? Again, this is a closing bracket, so we have to be careful. What do? We look at the value on the top of the stack. This is clearly not an opening curly bracket, so we'll go ahead and remove it, but we'll keep it on hold. Minus may be or may not be a part of a valid string. All right, so we have B now. Again, B is not an opening curly bracket, so we can't care about that. So B and minus are both at an intermediate state. We can't really say anything about them. But what do we get now? We have an opening curly bracket. In other words, we have found the opening for this closing curly bracket, which we are on currently. In other words, what does that mean? That means we have resolved everything in the middle of these two brackets. So you can see somehow that kind of structure is being followed again. We have sort of parsed the input. We're trying to understand how this input is laid out. All right. So now what do we do next? Let's go ahead and keep on iterating. So we get a star. Again, this is not a closing bracket, so we'll just add it directly. We get a C, not a closing bracket, add it directly. And now we get a closing round bracket. What do we do next? What do we do? Think about it. We're going to keep on popping these elements out one by one. We're going to keep on popping them out till we get an opening round bracket. And as soon as we get an opening round bracket, what do we know? We know that everything in the middle of both of these brackets is going to be validated. And this is the way we have figured out how to parse the input. We knew that we had to use a stack because we could see the leaf ordering being followed in the way brackets were opened and closed. And then we figured out how to exactly go about looking at the opening and the closing of brackets by using a left to right parsing. Now, a quick small implementation level detail is how do we implement this? In the previous example I showed you, we were appending these brackets and the pluses and the minuses directly. And you can do that. You can directly add the elements, or you can also add the indices. Now, different questions will require different cases, but in general, if you want one single template, just use indices. And that's because if you append indices to the stack, you will obviously have a mapping to the elements as well. But if you only append elements to the stack, you might forget which index it came from. Anyways, that's a very small level detail, but still important to keep in mind. Just make sure you are consistent with what you're appending to the stack, whether it be elements or indices, right? So what is the conclusion? Let's summarize this once more. We figured out in all the parentheses and the calculated questions, we have to use a stack. Why is that? Because these brackets were following a leaf ordering. Last ones to get in were the first ones to get out. They were the first ones to get resolved. And how did we figure out how do we use it? We know we have to use a stack, and we iterated from the left to the right, and we parsed the input. We figured out the input and the structure of the string that is given to us. And finally, you can either add elements or the indices to the stack. That's upon you. And that's a small detail you can take care of later on as well. All right, so keeping these three rules in mind, let's go ahead and work out a couple of problems to fully get comfortable with parentheses related questions. Hello everyone and welcome back. Let's talk about the problem valid parentheses on LeetCode. This, by the way, is a slight bit modification of the problem balanced parentheses on InterviewBit. If we are able to solve this, you will obviously be able to copy paste the code and get it accepted for balanced parentheses as well. Anyways, this entire solution is based upon the understanding from the previous video, where we talked about the introduction to all parentheses based questions. We figured out how do we use the leaf ordering, how do we go from the left to right and parse the input, and the way we exactly implement stacks. So if you haven't checked that video out, I'll highly recommend you do, because this solution is based entirely on top of that. In fact, it's going to be a very easy version of what we have seen before. All right, let me go ahead and show you and take you step by step throughout this problem. Given a string s containing only brackets, we have opening and closing brackets of the type round, curly, and square. And the goal of this problem is to return true if s is valid and false otherwise. So looking at the example cases, we have the first one returns the output as true because the closing and the opening brackets match and mix and match appropriately. In the second case, however, there is a stray opening curly bracket which never gets closed. In fact, it is trying to close the round bracket which is going to be invalid. So we have to return false in this case. All right, let's go ahead and talk about the intuitions and the observations needed to solve this question a bit more formally. We'll take the same test case and we'll try to build our understanding from this. Now, if we focus on the opening round bracket, we see that it gets closed towards the very end. We get a closing round bracket towards the very end. So both of them resolve each other out. All right, what about the opening and the closing curly brackets? Well, both of them again mix and match well. And this closing bracket is able to close the appropriate opening bracket. That is, the closing curly bracket wants an opening curly bracket to be present before it. And it is, so we can see that this is also a valid case. What about the square brackets? Again, the opening square brackets get closed by the appropriate closing bracket. So this is also valid, which means that everything inside of this test case mixes and matches well. The opening brackets are closed by the appropriate closing brackets. So we return true in this case, right? Let's take another example. And this time we have something more interesting going on, because we have the same number of opening and the closing brackets. That is, for one opening round bracket, we have one closing round bracket. For one opening curly bracket, we have one closing curly bracket. But the ordering in this case is messed up. That's because if you can notice, this closing round bracket is trying to close an opening curly bracket. Obviously, this will never work because this closing curly bracket, this closing round bracket wants to close an opening round bracket. It cannot close an opening curly bracket. So brackets in these cases do not match. And obviously, this is contrasted with the case where we have the same number of opening and the closing round and curly brackets, but one of them is invalid and the other is valid. So clearly ordering matters. And if you notice, the input has to follow this leaf ordering that we discussed in the previous video as well. That is, the last bracket to get in should be the first one to get out. And that was sort of the intuition behind using a stack. And we also discussed how do we go from the left to the right and parse the input. Let's go ahead and do that in the next step. One more thing, we also discussed that if the brackets open, add them directly. If the brackets close, check what they are closing. That is, if you get any kind of opening bracket, just add it to the stack without thinking twice. But as soon as you get a closing bracket, what do? As soon as you get a closing bracket, you have to check whether it closes the right opening bracket or not. All right, let's go ahead with a simulation. First thing we'll do, keep on iterating from the left to the right. We get the first element as an opening bracket. What do we do? Add directly, no thinking. Then we iterate forward and we get an opening curly bracket. Again, since this is opening, we'll just add it directly, no thinking twice. But now what do we get? We get a curly closing bracket. Now we have to be careful. We have to be very careful in what we do. Because as soon as we get a closing curly bracket, what do we expect? We expect that it closes an opening curly bracket, because no other case will work out. This closing curly bracket cannot close an opening round bracket or an opening square bracket. It can only close an opening curly bracket. So now, following that leaf ordering again, we'll look at the top of the stack. What is the top of the stack? It's an opening curly bracket. So that's great. For this current closing curly bracket, we found an appropriate opening curly bracket. In other words, both of them validate each other and satisfy each other. Pretty nice, right? All right, let's go ahead and continue iterating, and we get an opening round bracket. Since it's opening, we add it directly. But now what happens next? We get a closing square bracket. What does that mean? Well, this closing square bracket comes in and requests that, hey, can you get me an opening square bracket? Because that is who I can satisfy, right? I can mix and match well with the opening square bracket. So we go ahead and look at the top of the stack, and we see that it's an opening round bracket instead. What does this mean? This means that this closing bracket is actually invalid. And so this will invalidate the entire expression. As soon as we get one invalid case, one parentheses messes up. As soon as one guy messes up, the entire string gets cancelled. Think about it that way, right? Now, just another example is what happens if we had a closing round bracket? What would happen in this case? In this case, what would happen is we would be able to mix and match well with the top of the stack. So we can say that, you know what, this closing round bracket will be able to match with the stack top. Both of them resolve each other, and we can move forward with our lives. Again, this is a closing round bracket. We'll check the top of the stack. Is it an appropriate opening bracket? Yes, it is. So let's go ahead and close that, and we're done. Now, what do we see happening at the end? All of these brackets are validated. All of the opening brackets have been closed. And this is the reason why stack is empty. Remember, this is another important condition which you might miss. The stack should be empty at the end. And what it says is that all of the brackets that opened, which we put into the stack, remember, all the opening were put into the stack and all the closing were removing them from the stack. So if at the end the stack is empty, that is a good sign, because we were able to close all the brackets that ever opened. Now, what's another case that could happen? Let's say that we have another curly bracket towards the end. Now, this is the entire string. What would happen? In this case, we would add it to the stack, but this would never get resolved. In other words, it will be left alone, and it would make the entire expression, entire parentheses, invalid. Right? So it's very important for us to follow a couple of conditions. Let's go ahead and formalize the logic, and that should make a lot more sense. All right, let's go ahead and talk about the code for the is valid parentheses question. All right, so first things first, we'll go ahead and create a stack, which is going to be an empty list. Next, we want to create a mapping from the closing bracket to the opening bracket. That is, for this closing bracket, for a closing curly bracket, I expect an opening curly bracket to be present on the top of the stack. Right, this is something we've discussed already. We have to do the same for opening and closing brackets for all the kind now. All right, cool. So now that we have created the mapping, we can finally go ahead and start to iterate from the left to the right. So we'll go over all the characters in the string given to us. Now, first things we'll check is that if the character is an opening bracket, if it's round, square, or curly opening bracket, then don't think twice. Just append it to the stack, right? Because as soon as we get an opening bracket, we directly add it to the stack without thinking twice. This is something we've already established. Else what do we do? In the else condition, things get more interesting because now I have to say, you know what, check if the mapping of this character, if the mapping of this closing bracket maps to the correct value present on the stack top. That is, for a closing bracket that I have right now, can you check if it maps to the correct value, that is the opening bracket of curly type on the top of the stack? Because if it does, then it's good. Then it's good, right? And we'll say, you know what, since both of them match, both of them resolve each other. So I'm just going to do stack.pop. I'm going to remove this bracket that matched. All right, what do we do in the else condition? What do we say when there's a mismatch? As soon as there's a mismatch, I'm going to return false. I'm going to be merciless. As soon as you guys mismatch, I'm going to return false right away. Okay, there's one more thing that we need to take care of. See, I've tried to access the stack of -1 here. What have we learned up till now? You just cannot access this stack of -1 just whenever you want. You have to ensure if the stack exists. And only when the stack exists, you can do all of these operations. Well, what do you do otherwise? What if the stack does not exist? What if the stack does not exist and you have a closing curly bracket or closing bracket of any kind rather? In that case, that closing bracket is trying to close something that doesn't exist. In other words, we can just return false right away. All right, so at this point, are we done? Can we return true? Not so fast. This is where another mistake can occur. We have to ensure that the stack is empty. We have to ensure that the length of the stack is equal to 0. Why? Because we already saw this example over here. In this case, we reached the end of the iteration and we had one curly bracket remaining in the stack. And this curly bracket was never resolved. It was never popped out of the stack, which means that it still remains unresolved to this date. In other words, this entire expression became invalid just because the stack was not empty. And just to reframe, what does empty stack mean? Empty stack really means that all of the brackets that were input into the stack, all of the opening brackets that were ever inputted into the stack have been closed. All right, cool. So let's go ahead and run this code and this gets accepted. So let's go ahead and submit this once and we get it accepted as well. All right, cool. So this is it for the solution to the problem, valid parentheses. Hello everyone and welcome back. Let's talk about the problem, redundant braces on InterviewBit. Now, just a quick aside, if you haven't watched the video introduction to parentheses question, I'll highly recommend you watch it because we're directly going to use rules and logic that we formed in that video inside of this question, because we're going to apply things directly without talking about it much. That's going to make the solution a lot simpler. All right, anyways, let's talk about the problem statement first. We're given a string A containing operators, round braces, and letters. So we have a bunch of operators like plus, minus, multiplication, divide. Then we have a round braces. So we have the opening and closing round brackets and a bunch of letters. The goal of this problem is to return 1 if A has redundant braces and 0 otherwise. All right, so let's go ahead and take a look at some examples. How do they find redundant? In the first case, we have a redundant brace because we have two sets of round brackets wrapping the A plus B when we only ever need one. In the second case, we see that there are no redundant brackets because we're going to make use of every single one of them. So let's go ahead and take a look at some observations and logic from the test cases given. And really, there is just one single observation that we need to pull out from these. What is that? Let's try to build up to it. The first test case we see is A plus B wrapped in these two sets of braces. Why is there redundancy in this? Because instead of 2, we can just use 1, right? Let's take a look at the last test case. Here we have a simple letter A, which is wrapped inside of these parentheses, but it looks like we don't really need this. The example and the problem setter says that, you know what, this is a case of redundant braces because you don't really need to wrap A in anything else. And in the middle, we see that we have A plus B. In this case, there are no redundant braces. We're using every single thing. Now, what do you notice? There's actually one thing in common with all of them, which makes the solution work. And this is the central observation of the entire problem. What is the observation? The observation is there should be no operators in between these braces. So in the first one, you see between the first set of braces and the second set of braces, there are either no letters and no operators, right? There are no letters or operators. In the second one, there are both letters and operators. And in the third one, there is a letter, but there is not an operator, right? So we have to ensure that there are no operators between any two sets of braces. Because if we can make this condition work, then we'll have a case of redundant braces. All right, just a quick aside, what are some of the rules that we saw earlier? Rules, when did we decide when we have to use a stack? We use a stack whenever we see a leaf ordering being followed. And that is true for all parentheses questions. So in this question, we're also going to use a stack. How are we going to use it? We're going to go from the left to the right and parse the input. See what structure this input is following. And finally, how do we implement this? In this question, the elements are the bigger focus instead of the indices. So let's just focus on elements. Let me actually go ahead and show this to you. All right. As we discussed, there should be no operators between any two sets of braces. This is something we'll keep in mind as we go through the example. All right, so let's go ahead and iterate from the left to the right one by one. So let's say we have the first element and that's the opening bracket. So let's just push it onto the stack. Again, if we get an opening bracket, if we get an operator, or if we get a letter, we push that onto the stack. The only time we don't push an element onto the stack is when we get a closing bracket, because then we need to be more careful. Again, this is something I've already explained in the parentheses questions, the introduction to parentheses questions video. If you haven't checked it out, if you haven't understood it well enough, go ahead and dive into it once more. Right. Cool. So we'll go ahead and continue iterating. We get another opening round bracket. So we'll just add it to the stack. Now we get A, then we get plus, and then we get B. Nothing special. These are just opening brackets, operators, or letters. We add them directly onto the stack without any question. Only when we get a closing bracket, then we have to be careful. All right, so now that we have gotten a closing bracket, let's try to be more careful with what we do. What's the first thing we do? Well, this closing round bracket is looking for an opening round bracket to close. Makes sense? So we look at the stack top. Well, that's an element B. B is not really useful for us. So let's just go ahead and pop that and we'll keep it as an intermediate state. We don't really know if B is useful or not. And then we see a plus. Now, what does that mean? Look at the condition on the top right. The question wants that there should be no operators if you want to have a redundant brace. That is, if you can find an operator, in this case, we have found an operator, that means that the expression that we're going to enwrap in these two opening and the closing round brackets is actually going to be a non-redundant one. We need those braces in this case. Again, that is just how the problem is defined. So now since we have found an operator, let's go ahead and keep that in mind. And we'll keep on popping these elements out one by one again. So we pop out plus, and then we also pop out A. But now what do we have? On the stack top, there is an opening round bracket. And what do we have currently? The pointer is pointing to a closing round bracket, which means that everything inside of this has to be considered together, right? Now, since we found an operator, what can we say about this current highlighted section? We can say that this is actually a non-redundant case. So this is actually a valid case of how braces are being used. So let's not touch this. We'll just keep on iterating forward. So now we get a plus. Again, it is not a closing bracket, so we can just add it directly. No thinking. Again, opening bracket, good to go. C, good to go. But now we have a closing bracket. So let's try to be more careful this time. Now what do we do? The first thing we do is look at the stack top. We have an element C. Again, it's not an opening bracket. So let's just pop it out, keep it as an intermediate state. And now what do we have? We have an opening bracket. So we have found an opening bracket for this current closing bracket. What does that mean? That means that the entire highlighted expression is what we have to look at right now. But look at this. There was no operator that we found in the middle, right? There was no operator in this highlighted expression, which means that there are redundant braces. And that's correct. So this is what it means. We have found a redundant bracket and we can return true that yes, indeed, there are redundant brackets in this input. All right, so let's go ahead and take a look at the optimized solution and we'll go ahead and code this up. All right, so this is going to be the code where we start from an empty stack. Again, very simple. And then we'll go ahead and iterate over all the characters in the input string, right? Now, as I mentioned, what is the first condition? The first condition is if you get a letter, if you get an operator or an opening bracket, that is, if you get anything other than a closing bracket, just directly append it to the stack. No thinking at all. Alright, when it goes to the else condition, we have to be a bit more careful. So in the else condition, what we'll do is we'll keep a track of the count. And this count keeps a track of a count of the number of operators we have seen. Because remember, that is what is going to tell us whether a bracket or whether an expression inside of the input is redundant or not. So we'll start the count from 0 and we'll say, you know what, since we have found this closing round bracket, let's just go ahead and keep on popping these elements out from the top of the stack one by one till we get a opening round bracket, right? Till we get a opening round bracket. So we'll go ahead and say now if the popped is actually an operator, that is, if it's any of the plus, minus, star or division, if the character is any of these operators, then I want you to do count plus 1. In other words, since we have found a positive number of counts of the operators, whatever the expression is going to be a valid non-redundant expression. And of course, at the end of this while loop, we are going to do a stack.pop because we want to pop out this opening bracket. We don't really have any use for this at all. Anyways, now what do we do? Once we're done with this entire iteration of this while loop, we're gonna check what the condition is. We're gonna say if the count is 0, that is if the count did not change at all. In other words, we did not encounter any operators. If we did not encounter any operators, return 1. We have found a case of redundancy. And if not, we'll just keep on going forward again and again and again. And if throughout the entire iteration of this entire string, you find no such redundancy, then you can safely return 0. That is, the entire string is non-redundant. Right? So let's go ahead and test this out. It looks like it works. And we'll go ahead and submit this as well. Cool, so this gets accepted and this is it for the solution to the problem, redundant braces. Hello everyone and welcome back. Let's talk about the problem minimum remove to make valid parentheses. This, by the way, is a medium level question on LeetCode and we're going to use this problem to build up our solution for longest valid parentheses as well. In fact, this solution is going to convert that hard problem into an easy one. I'm not even kidding. Alright, let's go ahead and get started with the problem statement. So we're given a string that contains opening and the closing round brackets and lowercase English letters. The goal of this problem is to remove the minimum number of parentheses to make S valid. So in the first case, we see that there are 2 opening brackets and 1 closing bracket. And we see that we have to remove any one of these opening brackets to balance these opening and the closing ones out. Okay, pretty simple. And so what I've decided to do is I've decided to remove the first opening bracket and keep the second one. You can also do it the other way. Both of them are perfectly fine. In the second case, we have the input as 1337 wrapped inside of brackets. In this case, I have to remove no such parentheses to convert it to a valid string because it's already a valid string. All right. So let's go ahead and take a look at some observations and logic to build up to the solution. Now we already talked about this test case where we remove the first bracket. But I want you to notice one more thing. The question clearly mentioned that we can only remove brackets. That is, we have to remove the minimum number of brackets to make it a valid string. In other words, we're only going to remove brackets and never the lowercase English letters. Now this is important because what we can do is simplify our life a bit. What we can do is look at these characters instead as indices and we can filter out all of those characters which are lowercase English letters. In this way, we have simplified the problem quite a lot, and now we only have to worry about the brackets opening and closing. All right, so let's go ahead and talk about a couple of rules that we discussed previously. First was the thing where why do we use a stack and when do we use a stack? As soon as we see a leaf ordering being followed, we are going to use a stack. And in this question, it's a parentheses question, so we will use a stack. The second thing was how do we use it? Well, we're going to go from the left to the right and parse the input. That is, for every opening bracket we see, we'll go ahead and add it to the stack. And for every closing one, we're going to remove an opening from the stack. So both of them are going to resolve each other. This will make sense in a second, don't worry about it. And the third one is how do we implement this? In this case, it is better to use indices instead of elements. Okay, because we did a filtering out operation, which means that indices are going to be the way to go. All right, so let's go ahead and get that input set up. And now we have an empty stack with us. So what we'll do is we'll go ahead and start to iterate from the left to the right. So first we'll go ahead and look at the element 0. All right, so element at the index 0 is an opening bracket. So we're going to add it directly onto the stack. No questions asked. Then we move on and we iterate further and we find another opening bracket at the index 4. So we'll again add the index 4 to the stack. Oh, by the way, I'm adding these indices and you have to focus on getting these indices into the stack. The brackets are there just for the sake of demonstration and understanding. We're actually going to only have indices in the stack, not the brackets. Anyways, then we go ahead and we iterate further and we find that we get a closing round bracket. Now, what does this mean? We have found a closing round bracket, which means that it is going to satisfy the opening round bracket. So this 9 is going to get satisfied with the 4. Both of them mix and match together and will pop the element 4 out of the stack. This is the reason why you see 4 and 9 in the answer. Make sense? Now we reached the end of the iteration, but 0 still remains on the top of the stack. In other words, it never gets satisfied. It never finds any closing bracket to resolve it. So we'll leave 0 out. So the minimum remove to make valid parentheses is going to remove the element 0 from the input. Okay, let's go ahead and take a look at another example, and this one will really bring forward the core of the problem. So let's go ahead and start iterating from the first element. We see 0, which is a closing bracket. Now this closing bracket is going to close an opening bracket. But do we have an opening bracket on top of the stack? Well, no, we don't even have any brackets on top of the stack. We don't have any brackets at all, which means that this closing bracket will never get satisfied. It will be alone always and forever. So we're going to leave it and we're going to iterate further. All right, so now we get an opening bracket. Let's go ahead and add it to the stack. Pretty simple. Next iteration, we see that we get a 4. Now this 4 did what? As soon as this 4 got an opening bracket, it popped it out and satisfied both of them. So now both the opening and the closing brackets have satisfied each other, which means both of them are essential to be a part of the solution, right? So let's go ahead and continue iterating. Now we get 6 and this is an opening bracket. So let's just go ahead and add it to the stack. Then we get a 7, also added to the stack. And then we get a 9. What do we do when we get a 9? That's right, we'll pop out the 7 and now both 7 and 9 will satisfy each other. At this point, we have 1, 4, 7 and 9, which are the parentheses which satisfy each other. In other words, they form an essential part of the answer. However, 0 and 6 have to be removed, right? We had to remove a minimum number of brackets, and this way we have found 2 brackets to remove from the answer. Okay, pretty simple. But what would happen, say if I get 10, which is a closing bracket, just for thought process sake. As soon as I get this 10, what would happen? This 10 is going to satisfy the element on the top of the stack, which is the element 6. So 10 and 6 are going to satisfy each other. And so there is where we end the iteration. All right, let's go ahead and take a look at the optimized solution. And okay, cool. Let's go ahead and get started. Now, if you notice, what we have done up till now is have a differentiation between these blue and the green ones, right? The blue ones were ones that never got satisfied, and the green ones were the ones which got satisfied. So the first thing I'm going to do is create an array called isOK, which is going to be initialized with 0 for all the values of the string. In other words, I'm going to say none of the elements in the original string ever get satisfied. That is my initial assumption, and I'm going to build upon that later on. Now I'll also have an initial stack, and we'll go ahead and start iterating over all the elements inside of the string. So we'll first get its index and then the character for every single element of the string. Now if the character is an opening bracket, what do we do? If the character is an opening bracket, we add it to the stack without asking any questions. Now, what happens when we have a closing bracket? When we have a closing bracket, we'll first ask the question, hey, does the stack exist? Is there any opening bracket on the top of the stack. Because if there is, what do we do? If there is, we will pop that element from the top of the stack and assign its index the value 1, saying that this opening bracket which we just popped out is actually a 1. It is okay. It is a green value. As we saw in the case for 1 and 7. Both of them were opening brackets and they got satisfied by 4 and 9 respectively. So 1 and 7 both get this 1. And we also assign is okay of I to 1 as well, saying that because 4 was the one that popped out 1 from the top of the stack, 1 gets satisfied, but also 4 gets satisfied. So we're going to satisfy both of them. And what is the else condition? What if the stack is non-existent? What if we get a closing bracket and then we realize that, hey, wait a second, the stack is empty. So we can't really close any opening bracket. In other words, we'll just have to continue, unfortunately, skipping over this current I. Alright, so what's the final else condition? If we get an opening bracket, we append it to the stack. If we get a closing one, we check the stack for emptiness or not and figure out what to resolve. But there's a final condition which says, if you have English letters, well, go ahead and also continue because we don't want to mess with any lowercase English letters. What we are only going to mess with the indices of the parentheses. Alright, so at the end of this iteration is okay is the array which contains all the information. It is the one which contains the information of which all are blue, which all are 0, and which all are green. The green represents 1 and blue represents 0. Right? So let's go ahead and iterate further. Now the goal of this problem is to return the string. We have to return the string by removing the minimum number of parentheses. Now using this is okay array, we've already found out all the parentheses which are essential and which are non-essential. So what we're going to do is we're going to go ahead and build the answer character by character once again. Remember, all of this, what this tag did was to store the indices of the elements. And this is why the is okay thing worked out. Now we're going to iterate over the string once again. And we're going to ask the question, hey, is the character a bracket or not? Because if it is a bracket, and only if it is okay, only if it has been satisfied, then we add it to the answer. Because if it's a bracket and it has not been satisfied, we'll have to continue. We'll have to pass over this test case. Now what's the else condition over here? If the character is a bracket, then you'll have to check if it's okay or not. But if a character is not a bracket, that is, it's a lowercase English letter, then by default, you have to add it to the answer. Alright, anyways, at the final point of time, you go ahead and just return the answer. So let's go ahead and run the code for sample test cases and submit this. Alright, cool. So this is it for the solution to the problem, minimum remove to make valid parentheses. Hello everyone and welcome back. Let's talk about the problem, longest valid parentheses. Now, if you haven't seen the video on minimum remove to make valid parentheses, this question will seem out of the blue. However, if you have seen that, this question is just a breeze question because we're going to use the exact same logic as we saw in the previous one. All right, let's go ahead and talk about the problem statement formally. And we're given a string of just opening and the closing brackets. That is, we only have opening and the closing round brackets. The goal of this problem is to find the longest substring of valid parentheses. In other words, let's take an example. In the first test case, we have the opening and the closing brackets which form a length of 2, but then we have 3 opening brackets which never get closed. In other words, the longest substring of valid parentheses is just 2. Now the second test case is one where we have opening and closing bracket, and then we have a bunch of opening brackets, but then one opening bracket at the end gets closed. Now what is the longest substring of valid parentheses? We have in this case 2 sets of the length 2 substring of valid parentheses. Since both of them are of length 2, we'll just return 2 as the answer. Now, what can we say right away about this kind of question? This kind of question is actually twofold. We have to find 2 things first. First, we have to figure out what all parentheses are valid or not. Because once we have the valid parentheses in hand, once we know which of them are valid, which of them are invalid, we simply have to find the longest substring of them, right? So this is going to be broken down into 2 parts. And if you realize, the answer to the first one is something we've already seen. All right, since there's not a lot to go on, let's go ahead and just build up our logic from the previous question. As with the previous one, we'll set up an isOK variable that is going to be all zeros of the length n. In other words, it is going to say that, you know what, I'll assume none of the brackets opening or closing ever get satisfied. All of them are zeros. We'll also have an initialization of the stack, and then we'll start to iterate over all the characters in the string. As before, we'll check if the character is an opening bracket or not, because if it is an opening bracket, we'll just directly add it to the stack. What if it's a closing bracket though? In the else condition, it's a closing bracket, we'll have to check if the stack exists or not. That is, for this current closing bracket, because I've gone in the else case, for this closing bracket, does the stack exist? In other words, is there an opening bracket? Is there any opening bracket that you can find which had been put on the stack? Now, if you can find that is the case, well then go ahead and make both of them satisfied. That is, go ahead and pop the element from the top of the stack, which is going to be an opening bracket, and set its value to 1. That is, that opening bracket has been satisfied by this current closing bracket. And obviously that also means this current closing bracket has been satisfied. So we'll set isOK of I to be 1. In the off chance that the stack is empty and you get a closing bracket, well, that's just sad. We can't really do anything about that. I'm sorry. Anyways, once we're done figuring out which of the brackets opening or closing are valid or not, we simply have to figure out the longest substring of these valid cases. So what we'll do is we'll set up a count, which is going to be a running count of all the values. And we have an answer, which is going to store the maximum of all of these counts. So what we're going to do is we're going to iterate in the range of n. That is, we'll iterate over every single index and we'll ask the question, hey, is the bracket I'm looking at, is the current bracket okay or not? Because if it is okay, well, that's great news. Whatever the count was, increase its value by 1. Why? Because I've found the case of a valid parentheses. Right? So as soon as I know this current bracket is a part of a valid substring, go ahead and add 1 to the count. Else what do we do? If at this point of time there is a bracket which is a stray bracket which never gets opened or never gets closed, well then we unfortunately have to reset the counter from 0. Right? So the next step is then going to be simply taking a max of the answer in the count, because answer wants to store the maximum possible value of all the counts ever. All right, so this is it for the code. Let's go ahead and run it, and we'll go ahead and submit this as well. And cool, this gets accepted. So yeah, this is it for the solution to the problem longest valid parentheses. Hello everyone and welcome back. This is the start of a new section on calculator related questions. It builds on top of our previous work on parentheses related questions, where we discuss the exact reasons why we use a stack, how we use it, especially the left to right parsing method, and the implementation level details that we need to take care of. Now what I'm going to do in this video is establish that we just need 2 steps. That's right, just 2 steps we need to know to solve any calculator related question. In fact, both of these steps individually are interview problems on their own, which means that once we solve both of these questions, we'll be able to solve any calculator related question. That is like killing 3 birds with 2 stones. All right. So the first step is to parse the input from the infix to the postfix notation. And the second one is to evaluate the postfix notation. Now the first question that you should ask is, wait, what is the postfix notation? So let's go ahead and talk about the introduction to the postfix notation first. All right, let's go ahead and take a simple example. And let's say that we have this kind of string that we need to evaluate. Now the infix notation is formally defined as such. In the infix notation, the operator is fixed in between the operands. Again, the operator is the focus over here, and the operator is going to be fixed in between in the operands. Now what is the postfix notation? Formally speaking, postfix notation is where the operator is present after the operands. Now that might sound a bit unnatural given that what we have been looking at all throughout our life is the infix notation. This is the simple infix notation over here. And if I ask you the question, hey, how would you go about evaluating this kind of thing? What would you do? The first thing we'll look at is brackets. So we'll evaluate everything inside of the brackets. So 3 times 3 becomes 9. And so this is the expression that we have now. What do we do next? We realize that we have to do a division operation first, which means that we'll do 9 by 7 C-style division. So 9 by 7 will get rounded off to 1. And now we have 0 minus 1 plus 1. And since plus and minus are of the same priority, we'll simply cancel both of them out and say that the final answer is nothing but 0. Now what have we done over here? What we have done is simply apply a rule called BODMAS, which stands for bracket, order, division, multiplication, addition, and subtraction. This is a rule that was commonly taught in high school math and is the way we evaluate any sort of input given to us. However, there is a small catch. See, if you have brackets inside of brackets, those brackets inside of brackets need to be resolved first before you evaluate the brackets. And if you have brackets inside of brackets inside of brackets, then you need to resolve the innermost bracket first, then zoom out and then zoom out once again. You can see that this sort of nesting is what can give rise to such complicated expressions. And while the first one on the top is pretty easy to solve using the same infix notation, the second one becomes much more harder. And so the question arose whether we can write the expression unambiguously and we can solve it efficiently. That is, without having to worry about this BODMAS rule, is there a way we can write this expression? And secondly, is there an efficient way to solve that expression once you have written it that way? This is the idea behind postfix notation. The postfix notation simply says that the operator is present after the operands. In other words, if we take an example like this, where we have 1, 2 plus, it is equivalent to saying 1 plus 2. Again, I know this sounds unnatural, but bear with me for a second because something interesting is going to happen. Let's say if we have 1, 2 plus 3 star, what will that evaluate to? 1, 2 plus will become 3, and then we have 3, 3 star. In other words, we'll have 3 times 3. What we have done is 1 plus 2 inside of brackets that needs to be resolved first, and then we'll do times 3. Do you notice something? If we go back the other way around, we have figured out a way to write these bracketed expressions into non-bracketed ones. That is 1 plus 2 which had to be resolved first, which were present inside of the brackets. We found a way to write that without using the brackets. How nice is that? We were able to figure out a way to unambiguously write this expression. Alright, so this is the general idea behind using a postfix notation. And so we can finally formally talk about these two steps again. The first step was to convert and parse the input from the infix to the postfix notation, and that is something we're going to look at in the next video. And then in the next one, we'll look at how do you evaluate the postfix notation. Alright, so let's get started. Hello everyone and welcome back. Let's talk about how do we convert the infix to the postfix notation. As we discussed, the infix notation is one in where we put the operator in between the operands. That is, we fix the operator such as a minus between the operands such as 0 and 1. So we have something like 0 minus 1. In the postfix notation, we have the operator after the operands where we have something like 0, 1, minus. Let's go ahead and take a look at some examples to understand this better. In the case we have 1 plus 2 in the infix notation, it gets converted to 1, 2 plus. If we have say 5 minus 6, it gets converted to 5, 6 minus. And then if we have something like 1 plus 2 times 3, we have 1, 2 plus 3 times. Wait a second. 1 plus 2 times 3 will evaluate to 1 plus 6, which is nothing but 7. But if we actually evaluate this, it'll come out to be wrong. That's because 1, 2 plus will get evaluated to 3 first. And then we'll have to do 3 times 3, giving us the answer 9. This is in fact wrong. We are doing 1, 2 plus 3 times, which is wrong. So what do we have to do instead? We have to switch out the ordering of this plus. Because now what we have done is we have done 1, 2, 3 star plus, basically saying go ahead and multiply 2 and 3 first. So 2 times 3 becomes 6, and so we'll write 1, 6 plus. Now 1, 6 plus is what? It's nothing but 1 plus 6, which is 7. And so now we have the correct answer. But if you notice what happened over here, we realize something. The ordering of these plus and the star operators changed. right? We had 1 plus 2 times 3, and it became 1, 2, 3 star plus. So the ordering of the plus and the star operators changed, although the ordering of the operands like 1, 2, 3 did not change. There's something interesting which we'll come to very soon again. All right, so now we want to formally talk about how do we convert the infix notation to the postfix notation, right? So let's go ahead and try to work out the answer one by one. So using the BODMAS rule that we know, we can say that, you know what, let's go ahead and do the division operation first. All right, so we have to do B by C first. And how are we going to write B by C? We're going to write it as BC slash. All right, pretty simple up till now. Then what do we do next? We also realize that there's a B by C times D. We have to do times D in the next step, because that is the second operation we have to follow using the BODMAS rule. So how do we write times D? Well, BC by forms one single operand now. And so we have to multiply BC by with D. BC by is one operand and D is another. And so we can write BC by D star. All right, how do we handle the plus case and the minus case then? Well, let's go ahead and handle the plus one first. So we have A plus this entire expression. How can we handle that? We can write A in the front and plus the end. And then we have minus E towards the end. So we can write it as E minus. Right? So we have followed the BODMAS property and we have written down the infix to the postfix notation. In fact, if you break it down, we have something of this sort. First, we looked at BC slash, then D star, then A plus, and then E minus, following the BODMAS rule exactly. In fact, what we have done here, in other words, is that we have somehow implicitly encoded the information of the BODMAS rule into the postfix notation. Now, to evaluate the postfix notation, we won't need this BODMAS rule at all, because we have already encoded that information in the structuring of the postfix notation, right? Let me go ahead and explain that further. What we have done is that we looked at the BODMAS rule and we figured out that we have to first look at brackets, then order, then division and multiplication at the same level, then addition and subtraction at the next lower level, right? So this is something we've implicitly encoded into the answer. Look at the ordering of the operators. We have slash first, then star, then plus, and then minus. I also want you to notice another thing which I brought up earlier as well. The ordering of the operands, which are A, B, C, D, and E, remain the same from the infix to the postfix notation. Only and only the ordering of the operators change. It went from plus, slash, star, minus, that is, it went from a completely random ordering to a well-defined ordering, where we had division, multiplication, addition, and subtraction. So now the question is, how do we implement this? How do we make this happen using formal logic? What we're going to do is we're going to go ahead and use a stack to do this. Let me actually run a simulation and show you how this works. The first thing we'll do is we'll start to iterate from the left to the right. And so let's say that we get the first element as A. Since this is the operand and we don't mess with the order of the operands, we are just going to write it as a part of the answer directly. No thinking twice. You see an operand, you write it in the answer. That's it. As simple as that. What's the next step? The next step is to iterate further and we see that we get a plus sign. Since the ordering of these operators do change later on, we'll keep them in a stack for now and we'll see what to do later on. Right? So now we add this plus to the stack. Then we get the element B, and what do? Since B is an operand, we'll add it and append it at the end of the postfix answer. All right, cool. So now we get a slash. Now I'm going to ask you a very important question. Is it okay to put this slash after this plus? Or should we instead remove this plus first and add the slash later on? What should we do? Let's think about something that is going to happen. If you remember, stack follows something called the leaf ordering. The last one to come in is the first one to get out. And notice what the answer on the top right hand side says. The answer on the top right hand says that we have to have division, then multiplication, then addition and subtraction. That is, we have to follow this highest to lowest ordering in the postfix notation. That is something that we have to encode in by default. Now, if it means that we have to have the highest priority operators first and the lowest ones later on, Using this LIFO notation, what should be the ordering we follow in the stack? Again, the last ones to get in will be the first ones to get out. So if we want the highest ones to come first in the answer, we'll have to ensure that the highest ones are the first one to leave out of the stack. In other words, we have to say that the stack follows the lowest to highest ordering. So in fact, what we have right now, plus followed by a slash, is okay. Because in the edge case that we ever decide to remove both of these elements, first will pop out slash and then plus, which now exactly follows the ordering we want, right? So I think that should make a lot more sense now. So let's go ahead and continue iterating. We get the element C, and since this is an operand, we'll directly add it to the stack. Now, what do we do when we get a when we get a star operation? Remember the BODMAS rule. It says that first you resolve brackets, then order, then division and multiplication at the same level. What does it mean for us to get a division and a multiplication right now? This is nothing but going to hint us at the fact that this multiplication operator is actually going to take this division operator and kick it out, because both of them are of the same priority. And remember, what is the ordering of the stack? The ordering of the stack goes from the lowest to the highest. All right, we can't allow elements of the same priority to stick in together. So we'll have to kick out the slash, and only then we can add in the star. Again, if you look at it, it is still going to maintain the lowest to the highest ordering now, right? It only happens after we kick out the slash. And if you look on the top right hand side, we can see that, you know what, this is indeed the correct way to go. So we're thinking about this correctly. Anyways, let's keep on iterating further and see what happens. We get a D, and since this is a since this is an operand, we'll add it directly to the answer. Then we get a minus, and now what happens? The priority of minus is much lower than that of multiplication, which means that this minus is going to kick out the multiplication. You can think about it this way. You can think that an undeserving candidate comes, a lower priority element comes, and it kicks out all the higher priority or the equal priority elements out of the stack. It says that, you know what, you guys are much higher priority than me. Minus comes in and says, you know what, addition and multiplication are both either higher or equal to me. So I'll kick you both out. Let me just go and stay in the stack. So we'll go ahead and first kick out the multiplication operator, and then we'll again compare it with the addition one. So now we'll say, okay, you know what, since plus and minus are both of the same priority, let's go ahead and kick out plus as well. Then we'll add minus into the stack. Okay, so now we can go ahead and continue iterating, and we get the value E. We'll just add it to the answer, and then wait a second, we have reached the end of the iteration, right? After E, we have reached the end of the iteration. So what do we want to do? We want to empty out the contents of the stack. And since there is only one single element, let's just go ahead and add this at the end. So now you can go ahead and compare both of them and realize that, you know what, we were actually right. All of this logic worked out for us. So now we want to go ahead and formalize the logic and write it in terms of code. And we're going to follow the exact same things that I taught you before. First things first, let's create a postfix array, which will return at the end. And now we'll also create a stack for the operators. The stack is only ever going to store the operators and not the operands. Now we want to start iterating over every single element in the infix. And we're going to call this element token because it can either be an operator or an operand. We don't know yet. Now we'll ask the question, hey, if the token is not an operator, that is, if it's a letter or if it's a number, a digit, something like that, if the token is not in the operators, then what do? It means that the token is actually an operand. And in that case, we realize that we just have to directly append it to the postfix notation. We don't ask any more questions, and that is it for an operand. Now, what happens if we have an operator though? Then obviously we want to append this item to the stack. We want to push the token onto the stack. Remember, stack follows the lowest to highest ordering, which means that we have to write 1 or 2 lines of code more. And this is very important, and this is something we'll come to, by the way, in the next section as well. Okay, so let me explain what's going on here. I'm going to say while the stack exists, that is while there are elements in the stack, and the priority of the element on the top of the stack is greater than the priority of the current token. That is, we're looking at something like a minus, as the current token and the top of the stack is a star, which we had a case like that before. If we have a case like that, then this current token of lower priority is going to kick out the element from the top of the stack. And it's going to kick that element from the top of the stack. We'll do stack.pop, and whatever the element was kicked out is going to be appended to the postfix one directly. So we are going to say, while that is true, while the current priority of the token is lesser than equals to the priority of the element on the top of the stack, then keep on doing this pop operation. Because we are strict, we want to have a lowest to highest ordering. We can't even allow elements of the same priority to be there. Because even if the priority is same, we're still going to make a kick operation. We're going to kick that element out from the top of the stack and append it to the postfix notation. All right, cool. So this should make sense now because we have to follow the lowest to the highest ordering. Okay, what's the last step then? Are we done? If you remember, we had the case where there was one single element minus in the stack remaining at the end. So we'll actually have to handle cases like that as well. And we have to say, you know what, while the stack exists, while there are a bunch of operators in the stack, go ahead and pop that element out of the stack and append it to the postfix. Now, obviously, in this kind of case, we will only ever have one single element like that. Okay, anyways, all of this was to convert this kind of input as we saw on the top from the infix notation to the postfix notation. But now I ask you the question, is it possible to somehow include in brackets as well? Because look at the inputs. We have never talked about brackets up till now. We've only talked about operands and operators. What if there are brackets? All right, let's go ahead and write some more code. And since brackets are of higher priority, since, you know, in BODMAS rule, we always take care of brackets first. Let's go ahead and handle the cases of brackets in the first two conditions. So the first thing we'll say is that if the token is an opening bracket, what do? We will append this token on the top of the stack. We'll say, you know what? This is going to start off a new expression that we need to take care of earlier on. So let's go ahead and append this token on the top of the stack. Okay, now what? Well, we want to say, you know what? If the token is a closing bracket, then we need to do something more. As soon as we get a closing round bracket, what do we want to do? We want to take care of all the elements present between this opening round bracket and the closing round bracket. So what we're going to do is we're going to say, you know what? While the stack top is not an opening bracket, go ahead and kick out all the elements one by one. So what we are going to say is everything in between of these two brackets, between this opening round bracket and the closing round brackets, go ahead and pop those elements from the top of the stack and keep on appending them to the postfix notation. One last thing that we have to do. What is the one last thing? The stack top is currently now having the opening round bracket as the stack top. Why is that? Because that is when the while loop exists. Because the stack top is going to have the opening round bracket, which means that we have to take care of that once again. We have to do a stack.pop operation saying that, you know what, we don't really care about brackets in the postfix notation, because that was the whole point of postfix notation, to get rid of the brackets in the weird BODMAS ordering. Now let me ask you this one question. And this is a kind of a special trick case that we need to take care of. Remember the BODMAS rule, right? And what I promised at the start was that we will be able to somehow implicitly encode the information of the infix notation in the postfix notation, right? And we were able to do that by handling the cases of brackets separately and division, multiplication, addition, subtraction. All right. But now if I ask you, let's go ahead and also formally define the priority. What is that going to look like? Because we use this priority over here in the while loop, right? Now, how do we define the priority? Well, the priority will be a little bit different. So obviously the order has the highest priority, then division, multiplication, and then addition, subtraction. But the bracket, the opening bracket, will have the lowest priority. Why is that, you ask? It has a very interesting reason behind it. All right, let's say that we have a bunch of elements in the stack. Let's say there's an opening bracket, and now let's say that the operator is simply a star. So we have an opening bracket and a star after it. Now let's say that the minus comes. All right, so what is minus going to do? Minus is a lower priority element, so it is going to kick out the star out of the stack. But at the same time, we want to ensure that this minus does not kick out the opening round bracket, because it's not minus's job to handle that. It's the job of the closing bracket to handle that in its own while condition. So we are going to have opening bracket having the lowest priority so that the minus or any other sign in fact is never able to kick it out of the stack. All right, so in this video, we learned how to convert the infix notation to the postfix notation. Now I promise you in the next one, we're going to look at how do we evaluate the postfix notation, and that is going to be so much simpler than this code. Hello everyone and welcome back. Let's talk about how to evaluate the postfix notation. In the previous video, we looked at how do we convert the infix notation to the postfix notation. And I promised early on that the postfix notation is going to be a very easily computable way to get the answer for any calculator related question. What we're going to do is very simple. We're going to create a stack, and now we'll see that we're going to start iterating from the left to the right. Now for elements like 0, which we'll get as operands, we're going to push them onto the stack without asking any questions. As soon as we get another operand, let's say in the case of 1, we are also going to push it to the top of the stack. But things get a bit more interesting when we get an operator. Because now what does this operator mean? What does this entire 0, 1 minus thing mean? This means that we have to do 0 minus 1. In other words, we have to pop 1 out of the stack. We have to also pop out 0 from the stack, take their negation, that is do 0 minus 1, because we have gotten a current value as the negative minus sign. So we have to do 0 minus 1 and then put it back into the stack, right? So what did we do? You get an operand, you add it to the stack, no asking questions twice. But as soon as you get an operator, go ahead and remove 2 values from the top of the stack, do the evaluation, and then add them back in. Okay, let me continue and show you what this means. So we get 3. This is an operand, we'll add it to the stack. We get another 3, operand, add to the stack. What do we do when we get a star? As soon as we get a star, we'll pop 1 value out, we'll pop another value out, multiply both of them since this is a star operation, find the value, and push this answer back onto the stack. Okay, again, what do we do when we get a 7? Add this onto the stack. Now what do we do when we get a slash? What will be the next step? Since we have a slash, we're going to pop out the last 2 elements, 7 and 9. We're going to take their division, 9 by 7, and this is a C-style division, so we'll get the answer as 1. So we'll get the answer as 1 and we'll push this back onto the stack. And then finally, we have the plus operation where we'll pull out 1. We'll also pop out minus 1, add them together, get the answer 0, and then push it back onto the stack. At the end of this iteration, one thing is guaranteed. There will be only one single element inside of the stack, and that will be the answer. Okay, so what are the rules formally speaking? We do 2 things. First, if you have an operand, you add it to the stack. Else, you pop the last 2 elements, evaluate them, and then add their result onto the stack again. All right, so let's go ahead and look at the code implementation of the same problem. This is the problem evaluate reverse Polish notation, which is the same as the postfix notation on LeetCode. All right, what are we going to do? First things first, initialize a stack, right? The stack is going to be an empty list. I'm also going to define these ops, which is basically going to define for this character, for this current operator represented as a string, as a character, I want to do this operation. I want to do operator.add. For minus, I'm going to do the subtraction. For the multiplication, I'm going to do mul. And then for the division, I am not going to do floor div. Right? These are the 2 options with us. We have one as true div, which is just a slash, and the floor div, which is actually double slash. So it might look tempting for you to do double slash when it comes to Python code. Although in other languages, you can just do slash and get away with it. In Python, do not do double slash, because that is floor div. That does not work as intended as you want, and is going to give you issues when it comes to negative values. I won't go into much more detail in that. You can go check out some of the links down below. Anyways, what we're going to do next is we're going to iterate over these tokens given in the input tokens. So what was the goal? We have to first figure out if it's operand or not. Now we'll say if the token is not in the operators, that is, If the token is not of plus, minus, multiplication, or division symbols, that means it's a integer value given to us. So what we're going to do is we're going to convert that token to an int value and append it to the stack. All right, cool. So now what we're going to do in the else condition is when we have these kind of operators with us. So what we want to do is pop out two elements from the top of the stack, do the computation, and then append the result back into the stack. Now just a quick run through of what's happening. Note that the ordering of these matters a lot. We're first going to pop out n2 and then n1. Again, look at all of the simulation actually, which I didn't explain it back then, but it's something very important. Look at what we have done, right? So as soon as we get the plus operation, what do? We first pop out this element from the top of the stack, which is going to take the second place. And then we're going to pop out this element, which is going to take the first place. So this one we currently popped out. This guy is the n1 and the element on the right hand side is the n2, right? This makes more sense for division as well as subtraction because they are not exactly commutative. All right, anyways, first we'll pop out n2 and then we'll pop out n1. Whatever the result is, we're going to get it by using this ops of token. That is, whatever this token is, say it's a plus sign. So we'll go ahead into this dictionary and access this operator.add function. And this is going to take in two values again, n1 and n2. Whatever the result is, we're going to append it to the stack. Now, one last thing that we realized was that the stack is going to have only one single element at the end of this iteration, which is going to be the answer. So we return it at the end. And now let's go ahead and test the code out. So we'll run the code once. Okay, looks good. And we'll go ahead and submit this. All right, cool. So this works out. And yeah, this is sort of a formal implementation of evaluating reverse Polish notation. By the way, if this seems too fancy, you can write some manual code here as well. You can just say elif token is a plus sign. Just go ahead and do this, and result will be nothing but n1 plus n2 and something like this. And so you can do elif for all of these sort of cases, right? If that seems too fancy, you can do it this way as well. All right, cool. So this is it. And I'll see you in the next one. Hello, everyone, and welcome. In this video, we're going to implement basic calculator 1, 2, and 3, all using the same exact code. Believe me, I'm going to do a copy paste like nothing you've seen before. All right. So the first thing we want to do with basic calculator is realize that we have already written most of the code in these two functions. The first function is going to convert the infix notation to the postfix notation, and the second one is going to evaluate the postfix notation. Again, both of these functions have been covered in separate videos of their own, which each of their own intuitions, observations, and formal code that we wrote down. In this question, however, we have to write one more function, which is going to do the parsing or the cleaning up thing. So we're going to do and create a read function, which is going to take in the string and return us the infix notation. All right, that is the goal of this problem. Okay, why do we do this, by the way? Look at this. The input we are given is a string. And so we can have a case like 3 plus a bunch of spaces, 1 space times 337. Okay, so nothing too special, but you can see that this is a hard string to work with. Mostly because won't it be so nice if you can actually have a list of tokens that we need to focus on? That is, if you have something like, say, something that gave us 3, then something that gave us plus, then 1, then star, then 337. Won't it be nice if we have an infix notation laid out like this, right? This will make things a lot simpler because we don't have nasty spaces to deal with and all of the numbers have been dealt with. That is, 337 actually is considered as 337 and not 3, 3, and 7, right? These are some of the cases that we have to handle. And so what we're going to do is convert and read the string into the infix notation. So the infix notation is going to be a list which will return at the end. How do we go about making this happen? Well, we'll go ahead and write a while loop. So we'll say I equals to 0. And while I is lesser than the length of s, go ahead and keep on doing some computation. The first thing we'll do is clear out all the spaces. So if the s of I, the current character I'm looking at, If it's a space, well, just go ahead and ignore this. I don't really want to mess with this. Elif, what do we do? Well, in the case of space, we simply ignore. But in the case of operators, we can't really do that because we have to add these individual operators to the infix notation list. So what I'm going to say is if s of I is present inside of the operators, by the way, these operators is the variable over here, which is simply just the brackets and the multiplication division signs, blah, blah, blah. If the current character I'm looking at is an operator, well, then go ahead and add this to the infix list. So I'll do infix.append the current s of I. I'll also do I plus equals to 1. All right, what's the else condition? The else condition is some case where we have a digit like 2 or 234 or 345, things like that. So we have to handle cases like these separately, right? What I'm going to do is I'm going to create a number variable, which is going to be an empty string. And I'm going to say, you know what, while the s of I dot digit is digit, actually. So while the s of I I'm looking at is a digit, well, then go ahead and append this to the number. So I'll do number plus equals to the s of I. And once I'm done with this, oh, by the way, I'll also do I plus equals to 1 always. And once I'm done with this iteration, when this iteration stops, when I get either a space or an operator, I'm going to say, you know what, go ahead and stop at this point of time. And please go ahead and do infix.append the number. One thing that we always check whenever we write these while loops is whether s of I will actually exist or not. There might be a case where this I plus 1 might take it out of the length of the string. So we'll also have to say, keep it limited to that. While I is less than the length of s and this happens, then do these computations. Okay, so we're almost done, but there's one more thing that we have to keep in mind. And this is sort of a, well, kind of a pain implementation that we have to take care of. Because here's the thing, the minus could be used as an unary operation. That is in the case of -1 and sort of minus of 2 plus 3. All of these cases are valid. But in all of the codes we have seen previously, we did not handle these unary operations. So what is a hacky way around this? Again, this is going to be a very hacky way, but what we can do is we can add a 0 in front of it. So as soon as we get an unary minus, we're going to do 0 minus that thing. So in the case of -1, we'll instead write it as 0 minus 1. And instead of minus of 2 plus 3, we are going to write it as 0 minus 2 plus 3. This is going to make the rest of the implementation consistent with our logic. So we'll have to say, you know what, before you do this, please go ahead and check if the s of I is actually a minus sign or not. Because if it's a minus sign, then we need to do some extra steps before we can jump into solution. All right, when is this minus sign an unary operator? This is an unary operator in a bunch of cases. We have to say, first of all, if I equals to 0, then go ahead and do infix.append 0. That is, if this minus sign is the first thing you ever get in the entire string, if it is the first position in the string, then you have to append a 0 before you append this current operator. All right. But this is not the only case. All right. So we can have another case where we say 5 minus of -2. All right. So this is a case where the preceding element, where the element to the previous of this minus is actually an opening bracket. So we'll also have to take care of this condition and say that, you know what, if the current minus is at the 0th element is at the 0th place, go ahead and append 0 to the infix before you append the minus. Or we have to say, or if the s of I minus 1, if the previous element, if the previous character was an opening bracket, then what? Then you have to take care to also append the 0. By the way, just to make sure that this I minus 1 actually exists, we have to write one more condition and say that this I minus 1 should be greater than equals to 0, right? So pretty simple. And yeah, I think we're done now. Let's go ahead and run the code once. Oh, by the way, we still have to write all these functions now. So the first thing we'll do is go ahead and read the s string given as the input, and this will get me the infix notation. For the infix notation, I'm going to convert it to the postfix notation. So postfix equals to infix to postfix of infix. And finally, I'm going to return evaluate postfix. All right, cool. Let's go ahead and test this out. Hopefully it works. Ah, god damn it. Okay, it's a typo. Line 20 is digit. Okay, cool. Fixed. Again, hoping that we don't have any issues. Let's just hope we don't have any more issues. It's going to be a pain otherwise. All right, I'm going to go ahead and submit this. Let's hope. And great, we get it accepted. Cool. So now, as I promised before, we're going to do a massive copy pasting thing. I'm going to Control C, go here and paste this baby over here. Let's go run the code once again. Get it accepted here. All right, cool. Looks good. And once finally in the basic calculator 3, let's go ahead and do the submit directly. YOLO. All right, cool. So we get this code accepted in all the 3 questions just by using these simple logics. What did we do? We first read the input string and we sort of cleaned it up and converted the string to a list of tokens. Then we went ahead and evaluated and converted the infix to the postfix notation. And finally, we evaluated the postfix notation. All right, cool. This is it for this video, and this ends the string related section of stack questions. Next up, we're going to look at monotonic stacks, which is more of a mathematical side of stacks. All right.